Okay, so we have these climate models which are imperfect, but they're the best models we have with basically all the knowledge we have about the climate system and the equations which describe how everything works in the system. But how can we really rely on these models to predict what happens in the future? Well, how do we run these models? Let's first talk about how we actually get the results from these models. When we start running a model, the model takes time to reach some type of equilibrium. When we talk about equilibrium is, for example, the global temperatures. If we turn on our model, the temperatures will start to warm up as the sun starts to interact with the climate system. We can see this is a period we call the spin-up. The model has to spin up and to reach some kind of equilibrium, but eventually the temperature here, any value, if we're looking at the temperature, the rainfall, the pressures, will eventually become stable, and then we can see that we can take the last 5 years of the simulation, and here we can see a 20-year period of the model simulation. This is not 20 years of reality, 20 model years. The last 5 or 10 years, when we have constant temperatures around the planet, we can say this is the climate of the model. This is the control climate of the model. And then we can look at the temperature distributions in different countries, the rainfall, the number of heat waves, flooding events, and this represents the climate of today. If we then want to see what may happen in the future, we can do, for example, a double CO2 experiment. We can double the amount of carbon dioxide in the model atmosphere and start the model again. Again, we have to wait 15 years or so, 20 years until the model reaches a stable new climate, new temperatures, and then we can look at the difference between the new climate and our control climate from before. We can see how the temperatures have changed, how the rainfall's changed, how droughts may have changed, and this is the way we can actually see what may happen in the future, but this depends again on what our new climate will look like, what gases we're going to put in the atmosphere, how much gases, how fast are they going to change. So this is how we use these models to try to see what may happen in the future under different scenarios. So in order to predict the future, we need to also see how well these models can predict the present climate or the past climate. And here we have some simulations from models compared with observation, looking back in time. These were done, say, in 2000, 2004. So at the dashed line, to the left is what we know already of the climate of the past, and we can try to simulate these changes in temperatures. And notice that, for example, we know that there was volcanic eruptions in 1991, and so this dip we see here in temperature, both in the observations and in the model, we see the model can simulate this fairly well, the amount of the decrease in temperature, the timing of the decrease. And when we look also into the future, we can see what the models predicted from 2000, 2004. What do they predict for 2020? And that what was predicted is the black line on the right-hand side of the dashed curve. And the envelope, we see the light gray or envelope around the black line are basically the spread of all the different models we have from around the world. So some models are a little bit higher, a little lower, but the black line is the mean of all the climate models around the world. And what we see that the predictions from the early 2000s to 2020 match fairly nicely the increase in temperature which was actually observed, shown by the red line. Obviously, we didn't know that we would have certain events like El Nino, La Nina in the future, and so the models predict a fairly smooth line going into the future. But we know, for example, 2015 and 16 was a very strong El Nino, which results in warmer temperatures globally, and so the red curve shows a peak here where the actual models didn't predict that. But overall, we see that the models do a pretty good job at simulating the historic temperatures and the predicted temperatures into the future. If we look at other parameters like rainfall, here we can see on the top the map is actual observed rainfall patterns from 1980 to 1999. The color bar shows the amount of rainfall in different regions. This is the annual mean, so how much we get in an entire year. Obviously in the tropics, the blue areas where we have most of the rainfall. In the subtropical regions, the desert regions, we have very little rainfall. And the bottom plot is the same map, but the data from 23 climate models, global climate models or general circulation models, and it doesn't look too bad. The models seem to give the overall distribution of rainfall, Also, the amount of rainfall seems to agree by the color scale here. But there are differences. If you look in detail, you'll see that there are obviously differences between the observed rainfall and the models. The models are not perfect. They're the best tools we have to try to understand the climate, but they're far from perfect, both because of their spatial resolution, the core spatial resolution, and because there's some things we still don't know about the climate system. Now we can go even further back in time to try to see how good these models are and how reliable they are for trying to predict the future. And here on this plot, each point here is a different climate we've experienced on planet Earth. And we're going back even millions of years. If we look at the early Eocene, the pink box, this was a period when the temperatures were nearly 15 degrees warmer than they are today. Well, there weren't any people on the planet Earth there. We didn't have any Homo sapiens wandering around there. It was much warmer, a lot more carbon dioxide in the atmosphere. We know this from geological records. And so we know that it was close to 15 degrees warmer in the early Eocene. Can the model simulate that? Well, this dashed line in the middle shows an exact agreement between the models and the observations. The models shown the simulated temperature on the y-axis shows that it was also between about 12, 13 degrees warmer in the model in the early Eocene, based on what we know about the concentration of gases in the atmosphere, the solar radiation, albedo of the planet, etc. And reconstructed temperature is very similar. If we go to colder periods, like the last glacial maximum 20,000 years ago, in the bottom left on the blue point, we know from, again, glacial measurements, from isotopes, chemical measurements, that the temperature of the planet was about 6 degrees, 5-6 degrees cooler than it is today. And the models can also simulate this cooling, which was on the same magnitude, about 5-6 degrees cooler in the past. And if we come closer to the present, if we're looking at the mid-Holocene, mid-Pliocene, the last interglacial, the models can simulate the global temperatures fairly well in this whole spread of different climates that we've had on planet Earth. And so the models do a fairly good job at simulating the climate. Again, they're not perfect, but they do a fairly good job, and they're the best tool we have to try to look what may happen in the future. And again, we've seen this plot many times, that when we try to simulate what's happened in the last century, the last 150 years, we know more or less how the different parameters have changed over time: the greenhouse gases, the solar cycle, volcanoes, aerosols, which actually cool the climate. And when we put these into the climate model, again, we can see that the variability and the amplitude of the warming we've seen since 1880 to the present, the models can very nicely duplicate the observations and show actually quite a high agreement between the model simulations and what we actually see happening in nature. Now, what's nice about models is we can turn off various switches and knobs in the model to try to understand how the climate is reacting to natural forcing and also to man-made forcing. And what we see here is a simulation running models with no impact of man, so no increase in greenhouse gas. That's what we see with the green curve at the bottom. So going from 1850 to 2020, run the model with volcanoes, with solar cycle, with oceans, with everything else, and we see that the temperatures stay more or less around zero. Zero is not 0 degrees. This is the anomaly. So a change of 0 degree, no change if it's zero from the temperatures of 1850 to 1900. If we then increase, we add, in addition to the natural causes of climate variability, we add also the increase in greenhouse gases, then we get the brown curve. And what we see basically that until about 1950s, the brown curve and the green curves are more or less the same, overlapping. But from 1950s, 60s, we get this divergence, and the brown curve starts to rise dramatically, and the black curve is the actual observations, what occurred. So what we see here is that without the effect of anthropogenic greenhouse gases, without the effect of man on the atmosphere, we would not be able to explain the temperature increase that we're seeing until today. We can only explain it by including both the natural causes and the man-made causes, the rising greenhouse gases. And we see that at least from the 1950s onwards, the main impact of the rising temperatures is because of man-made activity on the planet and not the natural causes. So what's great about these models is we can actually separate out different effects. We can run the model once just with the natural causes, just with the volcanoes, together with the anthropogenic, the man-made impact, and this allows us to understand how each of the different factors is impacting the climate. We can also do this instead of on a global scale, on regional scale. So we can see here each of these plots in the top is for different continents, different regions of the planet. And again, the black line is the actual observed temperature changes in the 20th century. The blue curves, the blue band of color represents the average changes from all the models when we don't include the rise in greenhouse gases, only the natural forcings. When we include also the effect of man-made greenhouse gases, then we get the pink band of simulations, which matches much better the actual observations than just the natural variation of the climate shown in blue. And at the bottom, we can also see this divided by global temperatures, global land temperatures, and global ocean temperatures. Any which way you cut the data and the models, we always come back to the same bottom line, that from the 1950s, the global warming we're seeing can only be explained by man-made activity on the planet. We can even divide this up further. So on the left, again, we can see the different factors which have influenced the models' warming, which is shown by that brown curve in the background and the observations in the black curve on the top left. We can break them down again into the greenhouse gases and the aerosols and the volcanoes. But we can go even further, and we can divide the greenhouse gases on the right-hand side into the different types of greenhouse gases: carbon dioxide, the methane, N2O, the hydrocarbons, ozone, and then we can actually see how each one of these contribute to the overall global warming that we're seeing today. What we're seeing on this part, on the right-hand figure, is the radiative forcing. So again, if it's a positive value, it means that this factor is warming the climate. And if it's negative, which is generally shown in blue, it's cooling the climate. And when we look at them, at the carbon dioxide, the greenhouse gases, methane, all of these result in a warming of the planet and the climate. But we've spoken about volcanoes, the stratospheric aerosols, we've spoken about clouds and the impact of aerosols on clouds. These cool the climate. And we can see how each one of these impact the overall radiative forcing, which you can see in the bottom, which today is equivalent to approximately 1.1, 1.2 degrees of global warming. So again, today, based on the models and the observations, we can simulate and we can reconstruct the climate. We can understand what's causing this 1 degree warming, which we've seen, which was published in the 2021 IPCC report. This is a combination of both the warming from the greenhouse gases, but also some masking due to the cooling from aerosols and changes in cloud properties. But overall, we see the net warming is about 1 degrees, a little bit more than 1 degrees. And just to end the section on the actual models themselves, it's very appropriate that in 2021, the year that the 6th report of the IPCC was reported, the Nobel Prize in physics was given to 3 scientists who were kind of the forefathers of working on these climate models from the 1960s and 70s, especially Manabe and Hasselmann, who really contributed to our understanding of the climate system by developing these complex climate models that we use today to try to predict what may happen in the future. And it's appropriate that it's the Nobel Prize in physics, because these models are really based on the laws of physics. It's not just statistical models or empirical models. These are based on the laws of physics of how the climate reacts to changes in greenhouse gases in the atmosphere.